In the modeling industry, some very attractive people are placed in front of a tightly controlled lighting setup and photographed by people who know how to pick the right camera, the right lenses, and the right angles. And yet, after all that professional input to capture the best possible version of the model, they still feel the need to digitally touch up the photos. They paint out blemishes, enlarge features, and introduce a strong color palette. Advertisers know that digital image editing tools can make images look better than real life. But can we apply that to visualization imagery too? The process of post-production involves combining all of the assets produced or collected for a film production and making it look and sound as good as possible in the final product. This includes video editing, color correction, computer effects, soundtrack, and more. The first step in the post-production pipeline is called editing. Editing is the process of placing footage in a sequence that makes it clear and exciting for the viewer. When assembling a story, editing allows you to control the pacing of the finished film. An editor chooses among multiple camera angles covering the same action. They build narrative through flashbacks, foreshadowing, and cuts between characters and conversation. They divide a film's narrative into distinct chapters called scenes. The editing process is different for certain types of filmmakers. Many live-action documentaries have a 10:1 editing ratio, meaning 90% of the footage captured doesn't appear in the finished film. But for films made with computer graphics, capturing 10 times the footage you will need in the final product is not even a little practical for many reasons, not the least of which is that rendering is a lot more time-consuming than recording live-action footage. This is one of the reasons we rely heavily on the pre-visualization process. It allows us to create a working edit of the film from simpler imagery before we invest time in creating footage that won't make it to the final film. Keeping a working edit and iterating on it throughout the production process is always a good idea when you want to avoid creating footage that gets cut. Inevitably, a good edit will always trim the fat of your shots, but you can get much closer to an economical production process by planning your shots out well before producing them. The next step in post-production is compositing. Compositing is a process of layering and manipulating video footage, sort of in the same way Photoshop can edit a still image. It may seem redundant to use digital editing tools on images that were already created in the computer. Surely if you want things to be brighter or more colorful, you would just do that in the visualization software, right? Of course, we're always trying to find the best possible look in the visualization software. But sometimes visualization software has limitations of how tightly you can control the look of something. It is constrained by the ray tracing paradigm, so some visual features can't be quite as controlled as you would like. Sometimes different shots in the same film aren't developed side by side, and compositing is an opportunity to unify them. This could be two separate shots that feature the same or similar data, or two layers for the same shot that were rendered in different software. Often it can be difficult to get the same look for the same data rendered in different software, even when using the exact same color values, because of the way the software has implemented its ray tracing, lighting, and image formatting. And sometimes you want to give yourself the ability to change things later on without having to pay for the expense of completely re-rendering the shot in the visualization software. One of the compositing tasks you should consider for every shot is called color grading. Color grading is a process of tweaking the colors across the whole image. One piece of this is optimizing the brightness and contrast of the image. To make full use of whatever final display environment you're using, you will want to stretch the image's brightness profile so that its darkest pixel is completely 100% blackest black, and the image's brightest pixel is the whitest white. Another piece of color grading is adjusting hue and saturation, perhaps to give the whole image a warmer or cooler cast, or to make it feel more or less vibrant. These color decisions can be driven by the type of experience you want or by the narrative. In scientific visualization, we typically find that a very saturated color palette captures audiences' sense of natural beauty and inspires them more than a muted photographic palette. Audiences tend to like things that look like an exaggerated version of real life. Although this adage is starting to become a bit tired after years of wildly overproduced Hollywood blockbusters. Another major advantage to compositing is the opportunity to refine how light is captured in the final video. In visualizations that feature bright objects like stars, you will often see regions of blown-out, bright white pixels. These glare effects are theoretically exponentially brighter in the center of the glare than they are at the edges, but because even the dimmest parts are bright white, you don't get to see any variation. If the glare is stored in an image format like EXR or 32-bit TIFF that allows its RGB color values to be stored as numbers higher than the maximum of 1, you can reduce that blowout simply by turning down the brightness. If the pixels are all clamped at 1 though, as they would be in a more typical JPEG or PNG image, changing the brightness will make the whole glare region dull out evenly to gray, and may require you to re-render the image with a smaller glare. After color grading, there are some other very common compositing tasks. Bright objects in the scene often demand more attention beyond just reducing clamping. In a real camera, bright objects create artifacts on the lens called glow, glare, and flare. While many animation packages offer tools to create these effects in the render, you should not use them. These tools are notoriously difficult to design with, and they're not editable because they get cooked into your rendered imagery. Because these brightness effects happen on the camera lens in the real world, and not in the actual environment being recorded, they are better simulated in compositing software. Glow and glare are effects you want to create using an image mask. A mask is a special version of your render that is white in the regions of interest and black everywhere else. These mask images are typically faster to produce and can give you the exact region of your image that you need to produce a realistic glow. Masks are useful for doing math on pixel RGB values. For instance, if you want to turn a region of your image to black, you multiply the RGB values by 0 in that region by creating a mask image that is black in that region. Let's say you want to only make a certain object in your scene brighter. You can select it as it moves across the screen by rendering a mask of that object, and then dial up the brightness of the image region selected by the mask. Another compositing task you might consider is interpolation. You should always be very careful when adding detail where there isn't any, as this can lead to unintentional resolution artifacts. A sharp image may become blurry if you scale it up. But perhaps you rendered a foggy object and you know the blurry edges won't get too pixelated when scaled. Or perhaps you want to slow down the sequence by a factor of 2. Some compositing software includes temporal interpolation tools that intelligently generate in-between images to stretch out the sequence. These temporal interpolation tools can be finicky because they're operating on pixel contrast instead of 3D geometry, so they're best used only when you have run out of other options. Occasionally, we will use temporal interpolation on data that comes to us as 2D imagery, like this sequence of the Earth photographed by a satellite. There's only so much source data, so we need to stretch it out to get a more comfortable playback speed. This is also a rare case of compositing before designing the visualization, because we then take these images and slap them on a sphere for a more immersive scene. The composite is also your opportunity to add film grain and other effects like dirt on the lens, vignetting, and lens distortion. Many of these effects aren't always useful in scientific visualization, but common features of compositing software that you might find a use for. You can also use compositing software to add annotations like color bars and data attributes. Compositing software is usually scriptable, just like visualization and animation software, so it's possible to have text driven by external data. You can also correct errors and artifacts that make their way into your rendered footage. It's usually better to design around these issues in the visualization software, either by editing them or hiding them from camera, but sometimes they're unavoidable. Like retouching a model in Photoshop, you can target these data blemishes in compositing software and paint over them, blur them out, or replace them with similar adjacent imagery. The method with which you target the problem areas can get labor-intensive, and sometimes a mask will do the trick. Other times, you will need to use a process called rotoscoping, in which you track an issue one frame at a time. This process is extremely similar to Photoshop editing, except you might have to repeat it hundreds of times for each frame. Typically, we avoid rotoscoping unless it's absolutely necessary. One of the most valuable benefits of the compositing process is the ability to change design decisions for a fraction of the cost of a new render from the visualization software. This typically requires you to spend more resources initially to provide options later, but the added flexibility as you near a deadline is invaluable. For instance, if you render your imagery at a higher resolution than your final needs to be, you can alter the framing of the final images in the composite by punching in on the resolution you actually need. Some of the more interesting effects created in compositing come from image layers, sometimes called AOVs or arbitrary output variables. Many animation tools provide the ability to write any kind of scene data to image pixels, in addition to the common RGB values. That data might be the temperature of the object in the scene, or the position coordinates of the object. The more useful aspects of this feature are that you can delay design decisions on camera effects like depth of field and motion blur. Depth of field is based on an object's distance from the camera. So by writing rendered objects' distances from the camera to an AOV, the compositing software has all the information it needs to decide where to apply blur. This also allows you to change the strength of the depth of field blur. You can also use a depth AOV to create a sort of atmospheric depth fog. Likewise, by writing motion vectors to an AOV, we can apply different strengths of motion blur to a render. There are some even cleverer tricks you can use once you become accustomed to working with AOVs. A colleague taught us how he writes the identities of different atoms to AOV pixels so that he can decide in the compositing process the entire color design of the scene. In this molecular data filled with atoms, we can write out AOVs that store types of atoms and types of molecules to pixels. This means that we can decide how to color each type of atom, and even whether to color it by atom or by molecule. Many of these tricks become difficult with imagery that has fuzzy edges or transparency. When volumes, gradient shaders, and motion blur appear in your image pixels between foreground and background elements mix together. Beware that you might have to give up on compositing solutions if that's the case. Compositing is a whole art form of its own, and it takes practice to understand all the ways you can manipulate pixels. By editing and compositing your visualizations, you can take them that next step to beautiful digital perfection. Fun fact: rotoscoping is an extremely labor-intensive process. It's essentially creating a hand-drawn 2D movie, but it often needs to look as high quality as a live-action movie. Some great film effects have come out of the rotoscoping process, though. Many Disney films animated characters from Snow White, Alice in Wonderland, and The Little Mermaid over live-action footage. The entirety of the movie A Scanner Darkly was an eerie merger of animated lines over live-action footage. And even the original lightsaber effects in the Star Wars franchise were realized with rotoscoping.